All right, hello everyone. Okay, can I have your attention? How's everybody? Bad? Why? Easy? But 2 more weeks to go, right? You'll be fine. I know probably most of you are tired. I guess you are in your third or fourth year of the job. Consider it to be easy. All right, so let's continue with what left from the past. So next week we can move to a continuous system. One thing, again, this came up last week before the your midterm, and something that I learned, I should never put a midterm after a holiday or a break, because it means your life is going to be miserable, and also my life is going to be miserable, because I had to answer lots of emails. But the reason that I did that, because I wanted you to have more time to study, but next year, no. So yeah, always I think to make something to make the life of the students easier, but it makes my own life more difficult. Anyway, so maybe good for some because you had more time to study, maybe bad for some because you couldn't use your vacation or the break, but that break meant to be a study break, so you could catch up with the stuff before. So one thing was on this slide, some people asked if zeta is, that's from the past, the damping. If zeta is bigger than 1, it means you're going to get a complex number here, right? Omega d is omega n square root of 1 minus zeta squared, which is true, but already for this case, when zeta is bigger than 1, already I included that complex number here when I use the when I simplify the equations. So maybe so you don't need to be worried about that complex number. Maybe it's better to write it down. Omega d omega n zeta squared minus 1, just for this case. So the complex number I already is in the formula. Has been simplified formula like this. Right? So that's one case. So when we have damping, we have 3 scenarios: overdamped, underdamped, and critically damped. Underdamped, when zeta is less than 1, we know how to calculate xt, and we know what is our omega d. Omega d is omega n 1 minus zeta squared, right? And that's correct. When zeta is equal to 1, so we have this scenario, and our omega d and omega n, they are equal. or sorry, omega d is equal to 0, right? Yeah, because zeta is equal to 1. Scenario when zeta is bigger than 1, you ended up with a complex number. That complex number, already I included there, simplified everything. So the correct format is this one. I didn't write it like that because I didn't want to confuse you like omega d, but maybe it confused you more. Okay, make sense? Question? So that's one thing. If you don't have any question, another things that came up. Let's go to the slide that we so many stuff. Can't believe, did I teach all of that? Well, I hope you don't feel that's a heavy course and overwhelmed. So let's, this slide, there is one page free after that. Let's use that page. All right. So that's the page when I said vibration absorber, which we'll come back to it shortly. So a couple of things. One, okay, let's have a title, some notes for the past topics. Okay, so let me see, do I have something here? I try to do a drawing here. All right, so let's say that. Okay, this is mass M. And what do we have here is so we have a system like a base motion system that we want to deal with. All right. And let's put a spring there inside. All right, so let's assume we have a cart, and that cart, all right, let's assume for now we ignore its mass, or we don't care about its mass, and that car, we control it with xp, and that xp has a harmonic motion, v sine omega t. It moves left and right. And inside that cart, we have a mass m with a spring, and it can have a damping, but for now, let's stick just with the spring. So we can analyze this system two ways. All right. So one is that I have my coordinate. Okay, and just give me a moment here. So that's method number one. We select our coordinate x to be the absolute coordinate. somebody is outside or a camera outside and watching at this, looking at this mass and measuring its distance. Okay? It doesn't care where the cart it moves. It just look at mass m and measure it like absolute motion. Another coordinate is, I'll come inside and I put my coordinate inside. Let's call that one also x. Right? So two different coordinates. It depends which one we go. So if I pick the first one, I need to draw the free body diagrams and then the rest of the story. So my free body diagrams will be, so I have the mass, and the coordinate that measure its center. Right. So now when I want to draw the free body diagram, let's say the cart moves with xp, the mass moves with x. So how much spring is going to deflect? That's something that we need to carefully write down. Let me use another color so we don't confuse these. So my force here is going to be kx minus xp. So that's the free body diagram. Do you agree with that? So the cart moves with xp. We are outside. We saw that mass m moves with x. So the spring then deflects by x minus xp. I have a tension kx minus xp. That's my free body diagram. And this x, we know this is the absolute measurement. Something with respect to the ground. And we know that when we use the Newton law, sum of the forces equal to ma, this a must be the absolute measurement, absolute acceleration, not relative acceleration. So if I write the free body diagram for this one, I will end up with kx minus xp equal to m x double dot. I simplified the equations, so I ended up with mx double dot plus kx is equal to kb sine omega t. That's one equation. Let's do it for the second one. So the second one, now doesn't matter what is xp. Xp can be 1 meter, it can be 2 meters, it can be 10 kilometers, right? Still the spring inside create a force which is kx. Right? As I said, the cart can move for 10 kilometers, still the force is kx because we measure it inside the cart. So that's my free body diagram. And now if I use the Newton law, I have to write down minus kx is equal to m. Here is the acceleration term. What should be the acceleration? Remember again, you need to measure the absolute acceleration. You are outside looking at the whole things. So if you are outside looking at this pink mass m, right? So you will see it moves with an acceleration, which is x double dot plus x double dot b. All right. Again, let's say you put the camera outside on the ground and it look at this mass m. So it see that it moves with x plus xp. So your absolute acceleration then is x double dot plus x double dot b. So simplify that equation, you will get is mx double dot plus kx is equal to m omega squared sine omega t. Oh, we have a b as well, right? M b. mb omega squared. Remember, xb, we assume it is b sine omega t. I did the derivative twice, so it's going to be minus, go to other side, becomes positive, b omega squared, so that's correct. Right? So two equations, their form is different. Remember, in vibration, always we need to get to that standard equation that we have. This was our standard equation. Mx double dot plus Cx dot plus Kx equal to F0, sine or cosine doesn't matter, omega t. It is that this M, C, K, and F0, they will have a different form when I have a rotating system. So remember, in your final exam, you will may see let's say, a question that is combination of rotation, unbalanced mass, and base motion. So you don't need those formula that we developed for base motion or for unbalanced mass. You need to develop your own formula by getting to this standard form. I just need those to get those graphs just to explain the concept. However, you may see a different problem. All right, so let's say one of these problems, let's say this mass M inside, also it has a motor inside that rotates with an unbalanced mass. You should be able to draw the free body diagrams and solve it. So let's say if I use this standard formula for each of them, what do I will end up? So this one, I know my answer xt is x sine omega t, because I don't have a damping, so it is sine omega t, but if I have a damping, it has also a phi. Right, that's the standard form. And we know x has also a standard form, which is f0 over k. So let me write down everything's, yeah, more or less. 1 minus omega squared, zeta omega n. Please do this case with damping later yourself, but that's similar. Just add a Cx dot. So in this scenario, I will end up, because I don't have damping, I will end up with F0. This is my F0, right? So I will end up with KB divided by K, 1 minus omega over omega n squared, which gives me x over b equal to and this is what we call it M, the magnification factor. And many of you ask why M has different form, because we have different scenarios, or we have like this, choose to have different coordinates. It's up to us to select the coordinate that we want. Do we want a relative motion? Maybe in the second diagram that I did, maybe you are more interested in, let's say, the relative motion. You want to know how much it moves with respect to the car. Now let's find x for the second one. All right, so this is my equation that I need to solve. This was for the first one, and I ended up with this m. So let's say, what is the form of m for this one? So x still the same formula, but my f0 now has different form. This is my f0. So it is mb omega squared divided by k, 1 minus omega n squared. So x over b will be, let me write it down. So this is our standard form. So what we have here, x over b equal to omega n squared, 1 minus omega n squared. And now this is my m. Because some of you emailed and asked about question, I believe number 52, and you said why M has a different form. It is more like the rotating unbalanced system. The reason that it has a different form, because we choose X as a relative motion. Right? So to summarize what I said, we always need to start with a free body diagram, get to this standard formula, know what is M, what is K, what is C, and what is F0. And our formula always is the same. This is the response of the system, the steady state response. The formula for X is always like that. But because we have different F0, we may end up with a different form at the end. And something that we define as magnification factor, again, depends on the problem. Like here, we define X over V as magnification factor, implying that if I have a base motion that has the amplitude of B, maybe 10 millimeters, what will be the amplitude of the motion of the, let's say, the system that I'm interested in? Okay? I hope it's clear. What I encourage you to do, please solve the same things with the damping. It's important. And maybe as a practice for yourself, do maybe one question. Let's say you have a cart. And this cart let's assume that we excited with a base motion, xb equal to b sine omega t. Right? So that's the card we excited with the base motion, and it is on some roll or something. And inside that, let's say I have something that has mass m is attached to the card by A and C. All right. So this is exactly, let's call this one M, not capital M. So this is exactly the one of those problem 1 or 2. And now let's say inside we have okay, so inside these things, we have an unbalanced mass. Let's say this distance is E, and this mass, maybe let's call it, okay, now I need an extra M, E maybe, or MR, stand for rotation, or rotating. Okay? So try to solve that problem. It's now a combination of two things. One time solve it with a relative motion, one time solve it with absolute motion, similar to 1 and 2. Right? So, and like always, you need to start with a free body diagram. So you say, okay, I have, let's say, set this horizontal line as a reference. Call this angle theta, and you know theta is equal to omega t. Let's say this thing is rotating with speed omega. Okay, this mass is rotating with speed omega. So you know it's going to have a centrifugal force, and let's call that centrifugal force mr e omega squared. All right. So this MRE omega squared, you know, if you find its component, it has one horizontal component and one vertical component, which we are not interested. Let's say we constrain these things above and below, and we are just interested in its horizontal motion. Okay, so we don't care about the ups and down motion, just horizontal motion. Try to solve that example and try to find the magnification factor. So most likely, it's going to have a totally different form than what you see before, what you've seen before, right? Yes. Good point. So let's make it even more interesting. And that's not my fault. That's the Raymond, right? Raymond fault. So let's say that the base has the excitation of omega 1, and the cart inside, the mass inside, has the excitation omega 2. But at the very end, try to see if omega 1 and its omega 2 are equal. What is your result? So now you have two things going on. One, a base motion with a certain frequency, another one with an unbalanced mass with a different frequency. And then try to see if, for example, your omega 1 is equal to the natural frequency, what will happen? Your omega 2 is equal to natural frequency, what will happen? Maybe you can select some values and plot them if you are interested. But for now, focus on the free body diagrams and then the rest. All right, hope it's clear now. But please go back, check question number 52 or other questions. And in vibration, you shouldn't try to use one of those formula that we use for M. Again, those were just for concept for us to explain those concepts. Always we go back to our original formula that's safer and it's always more reliable and better. We get to this formula and we know the response of this one, the steady state response, and the form for X. These are standard formula. And we know the formula for phi or phi, the phase. So, and lastly, one more thing that I need to explain, but I need more room. So let's see. I can squeeze everything down there. All right, worked. Okay, so the second topic that I just want to quickly explain, this is the standard Newton formula that we know. F is equal to ma. You've seen it from, I believe, high school 10 years ago. So another way to write this equation is to write it as m. Instead of a, we write it as dv over dt. Okay, they are the same. Now I can go another step and write it as f multiplied by dt is equal m dv. And obviously we don't like dt and dv and we integral. So we ended up with force multiplied by time from, let's say, time 0 to some certain time. And this one from speed v1 to speed v0 to speed v1. So I have a mass m, all right? So I have a mass m. I apply a load for a certain period of time, for 1 second, 2 seconds, 10 seconds, right? From 0 to t. So maybe this mass initially had a speed, or maybe it was just stationary. So the first term, let's write it again, f multiplied by time is equal to m delta v. This one is called impulse. So I guess some of who had 305 with me last year, not the year before, the online one. So you had. So we had to, for the online, for all those labs, we had to do the lab in a box. So we sent box to students all over the place, right? So it was fun to design those labs. I don't know what the student thought about it. One test that they did, they use a walnut cracker and they crack walnuts. So they apply load on a mechanism, which we gave them. But one thing that was important is when you apply a load, let's say to crack a walnut, do you apply it like all of a sudden in 2 seconds, or you just apply it slowly with that mechanism that we gave it to them? And one thing that they had to calculate was the impulse, force multiplied by time. So always when you apply a force, it's important how long does it take to apply that. So it gives us something which is mass multiplied by delta V, which we call it linear momentum. This is an extra things. I'm just gonna at the end say that we don't really need that one. But just for the sake of because we teach it in Manu 265. Some of you guys, Alberto and Sis, and some around, you took 265, but the rest of you, maybe you, from your MEC 2, maybe you forget or maybe not. So that's the linear moment, which usually we show it by the letter G. Now, if I multiply it by a distance, let's say rho, the distance multiplied by ft, rho multiplied by m delta v. A distance from a certain point. So let's say again, I have a mass, I apply a load to it, and I take the moment of that load about a certain point. So this gives me m, or to be exact, m multiplied by time. M is a moment or a torque. And this one, we call it h, let's say about 0.0. And this h is called angular momentum. So in the solution manual, most likely you've seen one example solved by this method. But what I'm trying to say here, you don't really need this method. You can always use your original formula, F equal to MA. So we don't need that one. So because there was some question you asked, okay, what is this one? What is H? It was in the solution manual. H is nothing but the taking a moment of a linear momentum about a certain point, which we call it H. That's all. It's good to know, but for your exam, at least in this course, you don't need to use it at all. Always I like to go to the basic, use the Newton law, and that's it. Which I believe I emailed everybody the solution with the regular one last week. Any question around this, or we're good? Quiet, silent. So I assume that you're good. And just something that I again remember you asked. Now I want you to give it some thought. So let's say I have a pendulum, center of gravity G. This is point O. And this is theta. Okay. So a pendulum, we fix it to the ground at point O, and we have it swing very well plated. So the center of mass is G, and the mass is M. Let's say we have I bar or IG, and we know how to find IO. Is IG plus M. Let's say this distance is L squared. So we know how to write the Euler formula, which is sum of the moment about point O is IO theta double dot. Magic. So now this time, let's assume that point O is not fixed and it can move. And to make it even more interesting, let's say it moves with a base motion. Right, so the difference between the setup on the left and right, left is fixed to the ground, right point O isn't fixed to the ground. It moves with XP. And we don't care about the mass of that things because that things, the card, it just moves with XP. So something that, now I'm going to just write it, but I'm going to give you time to think about it. Sum of the moment about point O is not equal to IO theta double dot, but what it is. Give it some thought, and on Friday I'll explain it. Was another question some of you asked, but there was a card, a pendulum with a torsional spring, and you were confused how to solve it. But as a general rule, whenever a point is fixed, we can use the Euler formula simply as sum of the moment about that point is IO alpha. When it's not fixed, what should it be? Which if you go back to lecture number 2, I believe, or 3, I'll explain it. Because this scenario is one of those scenarios that point O is not fixed, or the whole thing is not fixed to the ground. It's fixed to something, but that something is moving. Right? Any question for this one? Are we good? And these are important things to know. This slide itself is important. Please give it some thought, spend some time carefully and think about all this stuff. Except this box over here, we don't really need that information. We'll make them even smaller. All right. So with that note, I'm just going to give you a moment to write down stuff. So Friday, I will jump to the last chapter of the course, which is an optional, let's say, lecture to attend, but I encourage you to attend. I will explain the software MSC add-ins, how the industry will like doing vibration now, and you do the complex system. So try to attend. I'm not going to record that one. The reason is in the past, always when I run MSC add-ins and Zoom, there was some difficulties to and crash. But try to attend. And try to finish your project and your lab because as of next week, we will move to the continuous system. The system will end the degree of freedom equals to infinity. Continuous system which means n equals to infinity. So we started with n equals to 1, right? Then you learn how to do for n equals to 2 or bigger than 2. Now time to go to n equals to infinity. Which is more fun, but it's a little bit challenging. So you better clear out your schedule. You need to spend more time, some math and stuff. Yes. That's vibration here. But we call it lots of material. But yes, I'm trying to attend the lecture. So that's like starting from next week, we have 2 weeks for the last part of the course. Sorry? Yes, yes. Continuous system will be your exam. It's an important topic. So with the time that we have, I'm just gonna, all right, 5 minutes. 5 minutes, we are gonna solve one important problems in industry, which we have to deal with it a lot. At least I just mentioned it, and then on Friday we'll continue discussing it. So here is the scenario. You have a system that, let's say for some reason, we don't want to use damping, right? Because remember, damping damps vibration, but also it creates some external force, not external, some internal force. But let's say for now, we just want to see if, without relying on damping, if we can get rid of the vibration that exerted, let's say, on a system that we have. This is our main system. This mass m. And let's say we have a base motion. For simplicity, let's say this base motion has y sine omega t. Harmonic base motion. What I want to get is, can I do something to end it up with x equal to 0? Too good to be true, right? We have vibration, but we want to get rid of that vibration without adding a damping, because we know damping does something. But if it is under damp, still it's going to be some vibration, or it's going to be large force to damp these things. So what can we do to get rid of that vibration? There is this idea of vibration absorber. And what is a vibration absorber is an external device that we put on top of this device, which by device is It's a mass MA stands for mass of absorber, and KA. So it's not, in fact, a device. It's just a mass and a spring. We put it on top of our main system. So we add that things. Now, it was a very smart things that people figured long time ago, that they figured adding this system, it does something to get rid of the main vibration. And what I want you to think about it is try to see what condition we should have that this MA and KA make this system to stay like no motion. The trick is assume that this mass M is fixed to the ground, because this is what we want, right? If X is equal to 0, assume that that mass doesn't move ups and down. So it is balanced. It means the forces coming from down and up, they must cancel out each other. So give it some thought. On Friday, I will first 5 minutes, I'll discuss this one. Again, this is an important topic and you need to pay attention to it, but give it some thought. And after that, we switch to atoms. That's all. Thank you very much for listening, and I'll see you on Friday.